So hi everyone, and thank you very much for joining this seminar series on normalizing flow. We have very good speakers actually today. First, Dimitris Kalatzis, who is a PhD student at DTU Compute here in the cognitive section. He will present a short introduction and some geometric perspective on normalizing flows. Then we will have Polina Kirichencko, which is also a PhD student at New York University with Andrew Gordon-Wilson. And she will present two of her very last papers about semi-supervised learning and out-of distribution data detection. And finally, Antoine Wehenkel, working with Gilles Loup at University of Liège, will explain us normalizing flows seen as a Bayesian network.
Yeah, so I guess we can start with the first speaker.
Yeah, exactly.
So if you, Dimitris, are ready and you are willing to share your screen, I have to stop mine, sorry.
Sure.
Okay. And thank you again, everyone, to be here today.
So can you see my screen?
Yes.
Perfect. Okay, so thanks for the invitation. Before I begin, I will run a very quick breakdown of what I'm going to discuss today. In the introduction, I will just speak about normalizing flows in general. It will be a very short run through how we train normalizing flows, how to interpret them, and so on. Then I will move on to flows defined on manifolds. When we know the manifold structure, how we can leverage that knowledge in order to define flows on them. And finally, when we lack that knowledge, how we can use normalizing flows to do manifold learning. So let's start. So normalizing flows allow us to estimate complicated probability distributions and, depending on the use case, build samplers for them by taking a base distribution that is easy to evaluate and sample from and transforming it into the data distribution. As in most settings in machine learning, we assume continuous IID samples coming in a data set of d-dimensional vectors, and our aim is to estimate the data density P of x. So we can express x as a transformation of another vector u, which we sample from the base density P of u. It is customary to call the space of vectors u the latent space. The transformation t is a smooth bijection, and that means that it is an invertible function and its inverse is also smooth. In this talk, I will be using the word smooth to mean differentiable. We train normalizing flows with maximum likelihood, which yields the change of variables formula that you see below. So let us, for a minute, unpack this, this expression. What the change of variables formula tells us is that we can express the density on X as a transformation of a density in U. In other words, we can use T to shape the density PU into the density P of X, as in the example shown in the image below, where on the left panel we have a standard Gaussian as P of U, and it is being transformed by T into the more complicated data distribution shown on the right, which is we take to be P of X. Another thing that can be sort of gleaned from the change of variables formula is that the change in density is a consequence of the change in volume caused by the transformation T, which is expressed by the Jacobian determinant term. So computing the determinant term is hard, since in the general case, it's an O of n cubed operation. So one of the things we need to keep in mind is that we need to construct the model in such a way that makes this determinant calculation tractable. This, of course, creates a trade-off between model expressivity and determinant tractability that we need to navigate, we need to manage. I'm sorry. So flow models can be composed, as can their inverses. We can easily compute the Jacobian determinant of composite maps simply by multiplying the determinant terms of the individual transformations. As a final note, it is standard practice to form chains of individual transformations to create more expressive overall transformations. In the example below, the density shown on the far left is being transformed by a flow model comprising 4 layers into the density that is shown on the far right panel. So with this, we conclude the very short introduction to the basics of normalizing flows. Moving on to flows defined on manifolds. Up until this point, we have discussed the basics of flows that are defined in Euclidean spaces. Some types of data, however, do not intrinsically reside in Euclidean space. For example, our data might be angles, which are more naturally represented on the circle, or particles on surfaces with periodic boundaries, which are best represented on the torus. Or we might even be dealing with tree structure data, hierarchies, which are best represented in hyperbolic space. So in these cases, we need to extend the definitions of our Euclidean models to manifolds. And if we have information about the manifold structure, then it becomes relatively easy to do that. And we'll begin with flows defined on the circle. So in the paper, Normalizing Flows on Tori and Spheres, Resende and collaborators proposed using the Mobius transform as a flow on the circle. So let's see what this is. Let me know if you can see my cursor. Okay, good. So for this transformation, we will view the circle as a 1D manifold embedded in R2. For any point Z on the circle and another point omega, which has norm that is strictly smaller than the circle radius, we draw a line from Z through omega, which intersects the circle at another point G omega Z. Now, the Mobius transform is the antipodal point H omega Z of G omega Z. But one might wonder why this transformation is even useful. So what the Mobius transform does is that it takes the regions on the circle that are close to omega and expands that space, whereas it contracts the rest. And that has, as a result, the transformation of uniform densities to unimodal densities on the circle. So in order to turn the Mobius transform into a valid diffeomorphism acting on angles on the circle, we will leverage the structure of the manifold itself. Any flow that is defined on the circle needs to satisfy these 4 conditions, namely that points 0 and 2 pi are mapped to themselves, that derivatives are strictly positive, and that the derivatives at 0 and 2 pi need to have the same value. So the Mobius transform, as we've set it up, already satisfies conditions 3 and 4, but it doesn't satisfy the rest because it doesn't leave theta equals 0 invariant. And in order to satisfy the first 2 conditions, we will define a rotation that will map H10 back to 10. So that will result in a transformation in a valid diffeomorphism for angles that satisfies all of these conditions above. For the next model on the circle, we will take, one option we have is to take models defined in Euclidean space and to adapt them on the circle. Resende et al. Showed how to do that for rational quadratic spline flows. Rational quadratic spline flows were first introduced by Durkan et al., and they are piecewise functions from R2 itself. To construct such a transformation in an arbitrary interval -b to b, we pick k+1 knot points. And then these will partition this -b to b interval into smaller subsegments. Then for these smaller intervals, we pick k strictly positive slopes. And finally, we compute the transformation piecewise for all k sub-intervals. To adapt spline flows to the circle, as before, we will do a bit of extra work. First, we pick our interval to be 0 to 2 pi by first setting x0 and y0 to be, well, 0, and xk and yk to be 2 pi. And this satisfies conditions 1 to 3. Then we will set S1 to be equal to Sk, and we satisfy condition 4. And with that, we have what we need to adapt the RQ spline flow to the circle, and we're good to go. We can also extend flows to products of manifolds. For example, in this case, we have the torus, which is the torus in d dimensions is a product of d circles. Resente and collaborators used the flows they defined on the circle as building blocks for defining flows on the torus. Any density on the torus can be decomposed in an autoregressive manner as is shown. And we can model each conditional density with a flow model where we make the parameters psi functions of all previous dimensions. Finally, the joint transformation is a valid autoregressive flow on the torus. Moving on to the last section, manifold learning with flows. A little bit of motivation first. So the manifold flows we have seen thus far impose strong priors with regard to the topology of the spaces they are defined on. But typically, and for most interesting data out in the world, we do not have this information. So a question to ask is, can this structure be learned? Is it discoverable by the models we currently have? An advantage of flows is that they are exact likelihood models. That is to say that we can compute the density exactly without having to lower bound it or approximate it in some way. But the problem is that this density occupies the full data space RD. As such, they are not appropriate choices out of the box to estimate densities that live on low dimensional manifolds. So as an example of this, we have the image that is shown, where on the left panel we have a usual Euclidean flow that is used to estimate the density of points on a curve that is a 1D manifold embedded in 2D space. And as you can see, the model assigns density of the manifold. Ideally, we would like to have a model that only assigns density on points on the curve, as is shown in the right panel. Before we discuss how to build such a model, we will very briefly go through some basics on smooth manifolds. So first, informally, a manifold is a space that locally resembles Euclidean space. A hopefully intuitive example is the Earth itself. The Earth can be seen as a sphere, but for its inhabitants living in extremely local neighborhoods on Earth, it looks flat. So this resemblance to Euclidean space is formally expressed by the manifold's coordinate charts. Coordinate charts are pairs, they're tuples U phi, containing an open subset on the manifold U and the map phi, which we call a homeomorphism. A homeomorphism is a continuous invertible map with a continuous inverse. And this homeomorphism maps between U and an open Euclidean subset U hat. Intuitively, you can think of homeomorphisms as providing a unique and continuous way of mapping between regions on the manifold and Euclidean space. So homeomorphisms are enough to concretely define topological manifolds, but if we want to do anything interesting in our manifolds, such as estimate densities and differentiate through density functions, then we need to be able to do calculus on them. So we need to impose further structure on our manifold. So how do we do that? First, we want our coordinate maps phi to be diffeomorphisms. That is smooth as opposed to simply continuous maps, which are invertible and they have smooth inverses. Second, given another overlapping chart V psi, the composition of psi with phi inverse needs to be also a diffeomorphism. So now recall that flow models are smooth bijections and they have smooth inverses. And if that rings a bell, which hopefully it does, that's because we just defined this class of maps. They are diffeomorphisms. As such, flows are the perfect fit to model the coordinate maps phi of smooth manifolds. A further advantage is that we get the transition maps. Sorry, is there a question? Nope. Okay, something stray. As I was saying, an advantage is that we get the transition maps essentially for free, in the sense that we don't need to devote computational resources to modeling them explicitly. Consequently, we can learn any smooth data manifold by learning its coordinate charts. So Bremer and Kramer proposed a model they called manifold flow, which learns topologically trivial manifolds, that is, manifolds that are homeomorphic to Euclidean space, which are embedded in some higher dimensional ambient space, as well as densities on them. Such manifolds need only a single chart to be described with. So the model first learns the density on this chart, and then the mapping G, which maps the density on the embedded manifold, but it preserves its topology in the process. In other words, in this construction, we learn the density on the manifold, an embedding, and implicitly the coordinate chart for that manifold. So mathematically, this construction looks like as follows. First, we learn a Euclidean flow from the latent space U tilde to the chart U hat. Then the density in the chart is computed in the usual way that we saw in the introduction. This is a simple change of variables for now. Second, we augment our space in U hat with the variable V with extra dimensions, big D signifying the dimensions in our ambient space, minus small d, which are the dimensions, the intrinsic dimensionality of our manifold. So this will help define our embedding. That is a map that takes us from our chart U hat to the ambient space RD, but in a way that preserves the topology of our manifold, and it is invertible in the subspace that is our manifold. We will construct a flow F that takes our augmented space as input and maps it to the ambient space RD. The coordinates on the manifold we denote by U hat, while V denotes the ambient or of the manifold directions. Then to construct the embedding G, we simply zero out the dimensions in the V variable. To get the inverse of G, then we first invert F and then project to the manifold coordinates. Finally, the density on the manifold is given by this sort of ugly expression. So to unpack it, the red highlighted part of this expression is due to the density estimation with T. And while it doesn't it doesn't really show it, it's still the usual change of variables. However, the light blue part is due to the embedding, G. And in the light blue part, we have used a more general form of the volume term because we map from a low dimensional to a higher dimensional space. So the usual change of variables would not cut it. It would not accurately represent the volume that is being transformed. So for some qualitative results on this paper, on the top row, in the leftmost panel, we have the ground truth for a Gaussian density defined on the circle, where the bright yellow color denotes high density. In the middle panel, we see a Euclidean flow that does density estimation, more or less, but we see how it assigns quite a lot of density off the manifold. In the rightmost panel, we see manifold flow, doing a much better job of learning the manifold and the density, at least for the regions on top that have a higher density. There are basically more points to learn from. So in the bottom row, we see the Lorentz attractor system with ground truth trajectories and points sampled along these, and it is shown on the leftmost panel. And the middle and rightmost panels show different perspectives of samples that that we sampled more or less from the manifold flow, which was trained on the Lorentz attractor. An advantage of this construction is that we can plug in known flow architectures that we know work for natural images to estimate densities on natural image manifolds. And this is shown in the image that you see. And so, can we do more? A shortcoming of manifold flow is that it cannot learn manifolds with non-trivial topology, since these are not homeomorphic to Euclidean space, at least in a global sense. So in these cases, we need to learn a collection of coordinate charts, formally called an atlas, to properly model non-trivial manifolds. And this is something that we're currently working on along with Jesper Wollert and Søren Hauberg. And what I'm showing here are two examples on uniform densities on the sphere and on the torus. The model consists of 4 charts, and each point that is sampled is colored according to the chart it belongs to. A further advantage of this construction is that it avoids a known issue with flows, namely that they become numerically non-invertible due to the topological mismatches between the latent space and the data space, that is in the typical vanilla case. So to conclude, we saw that flows are exact likelihood models based on invertible transformations of distributions. We saw a couple of examples of how to extend them to manifolds when we know what our manifold structure is. And then we saw how to extend and how to use flows in order to learn the topologies of unknown manifolds. So this was pretty much it. Thank you very much for your attention.
Thank you a lot, Dimitris. Do anyone has any question about this talk? So you can either maybe unmute yourself or just ask questions in the chat if you want. I might have myself a very naive question. So you said, for instance, that like in practice, people tend to use a composition of function to do a transformation. And I just wanted to know if you have like, you will know the number of functions to get this transformation.
Right. That's a good question. This depends a lot on the problem. It's really, well, it's really data dependent. So simpler densities might require much fewer layers than something like, for example, natural images. It's one thing estimating some toy density on a very easy manifold, for example, that is homeomorphic to keep the theme to Euclidean space, and it's a whole different thing to do natural image modeling. So again, just to drive the point home, it depends very much on the problem.
Thank you.
Yeah.
Okay, so if anyone has any questions, we can go on in case. Otherwise, feel free to write in the chat, because we were using Slido, but we didn't advertise you about that. So
so we will maybe continue.
Yeah, so we can go on to the
program. And so the very next speaker will be Polina, and she is about to present two of her last papers. So Polina, if you're ready, You can share your slides whenever you want.
Yes, can you hear me well, actually?
Yes.
Okay, great. Right, let me present. So can you see my screen?
Yes.
The slides?
Yes. Perfect.
Okay, great. All right. So hi, everyone. I am very excited to be speaking at the seminar, and I wanted to thank Alison and other organizers for inviting me. Yeah, I'm Polina. I'm a third-year PhD student at NYU, working with Andrew Wilson, and today I will talk about two of our recent papers, but actually we might only have time for one, so we'll see how the presentation goes. And the papers are on normalizing applications of normalizing flows. Right, why does this not work? Okay. So the first paper I'm going to talk about is why normalizing flows fail to detect out of distribution data. And it's appearing at NeurIPS this year, and this is a joint work with Pavel Ismailov and Andrew Wilson. Right. So in many safety critical applications, such as medical, financial, or autonomous driving, it is very important to detect anomalous data on which model cannot make reliable predictions. And one possible approach for doing that is to use a likelihood-based generative model, which approximates the target data distribution. So for example, we could take a generative model and then train it on some trained data set that we have, and then choose a likelihood threshold on a validation set such that during test time, when we classify inputs, we detect the anomalies if the likelihood of the input falls below that threshold. So as Dimitris explained earlier, normalizing flows are very flexible deep generative models based on invertible neural networks. And for them, we can compute the likelihood of the data exactly. And so in this paper, we specifically focus on the type of the normalizing flows, which is based on coupling layers, such as real NVP or GLOW, and they are very popular architectures as they offer both fast sampling and fast density computation. And since normalizing flow offer the exact likelihood, it would be attractive to use them for this anomaly detection problem. However, in the paper from Naliznik and collaborators, it was shown that normalizing flows often assign higher likelihood to out of distribution data sets. So for example, in this figure, we show the distribution of likelihoods of a real MVP flow that was trained on fashion MNIST. And for out of distribution MNIST dataset, the likelihood is higher on average. And this is quite surprising at first, since the MNIST images are semantically very different from fashion MNIST. So MNIST consists of the handwritten digits and fashion MNIST of images of clothing. But in fact, most structured images for this model would be assigned with quite high likelihood, regardless of their semantic content. So let's discuss why it actually happens for the normalizing flows that the data that is very unlike trained data is assigned with high likelihood. So we argue in the paper that the answer to this question lies in the inductive biases of the flows. So in principle, when we're training the generative models with maximum likelihood, so when we are finding the parameters for the flow, optimizing the total train log likelihood of the data, this objective encourages the model to put all the probability mass on train data set. So if we imagine the flow would be infinitely flexible, it would just collapse to the train data and would be like a direct delta distribution on the train examples. And in particular, the test images would get zero likelihood because it is strictly suboptimal to assign non-zero likelihood to them according to the train objective. However, it is not the case in practice for normalizing flows. They have fairly similar likelihood on train and test. And so it is important to know that for solutions which are not achieving the global optimum of this objective, we may get many different solutions which have the same train error, the same train likelihood on the train data set that we have, but they assign the rest of the probability mass differently outside the train. And on this figure, we schematically show two models which are trained on this faces data set, and the train data points are shown with crosses. So here, here, and here. And the yellow model, it assigns high likelihood to semantically, for example, the face images and the face images corrupted with noise. And it assigns low likelihood to semantically different images, such as the images of animals or numbers. And so this is perhaps how like humans would assign likelihood if we were to distinguish face data set from non-face data sets. And this model would be well suited for OD detection. On the other hand, we have the red distribution that assigns high likelihood to all structured images. And it assigns low likelihood to the corrupted images that have semantically the same information as the face images, which is our trained data set. So this is basically the behavior that we see for normalizing flow for this red distribution. And these two models can have identical train likelihood. So the maximum likelihood training itself does not tell the model which data is out of distribution and which data is not out of distribution. So it is the inductive biases of the model which are captured by the design choices and the architecture, which determine how the probability mass is assigned outside of these train samples, and consequently how the model performs in OD detection. Right, so let's talk about the inductive biases of flows. Our first observation was that the latent representations, so these, the flow, it transforms the data space into the latent space, which usually has some simpler distributions such as Gaussian. And yeah, the first observation is that these latent representations, they don't encode any high-level semantic information about the images, but rather directly encode their visual appearance. So in these two figures, we show in distribution and OD images, and they are corresponding latent vectors for two models. So this was a real MVP trained on fashion MNIST, and MNIST is OD data. And this flow is trained on Celebe, and SVHN is OD data. And so we can recognize the inputs in their latent representation. And this is basically the sort of key observation here. So for example, like here on this latent representation for out of distribution MNIST digit 7, we can see the edges of the input. And it's even more visible for the other transformations of the latent. So for example, this one is the representation averaged over different samples of dequantization noise. So dequantization noise is something that is, it's like a very low magnitude noise that is added to the train inputs so that the image space is not discrete, but rather real valued. And so if we average, if we take different samples of dequantization noise, which should not affect the model's output too much, and we average a lot of these noise samples, then we get this pretty visible shape of the input in the latent vector. And another interesting observation is that if we use batch norm in real MVP in the train mode instead of the test mode, so that would correspond to taking the current batch statistics versus taking the accumulated statistics, we can very clearly see the input in the latent space only for out of distribution, but not for in distribution images. And it's pretty much the same for the colored images for Celeb A versus SVHN. So the question is, why does this happen? Like, why we take a flow which performs a very nonlinear, complicated transformation using millions of parameters, and we get that the latent code very much resembles the input. So let's look into more details of the architecture of the flow. So the normalizing flows like VLNBP, they consist of sequence of building blocks called coupling layers. And they have a certain structure which ensures that it's easily invertible and the determinant of the Jacobian is tractable. So in the coupling layer, the input is split into two disjoint parts, XID and XChange. And then the first part, XID, is just copied to the next layer directly to YID. And the second part, XChange, is changed with an affine function where the scale and shift are predicted by a neural network like a ResNet based on the XID part. So yeah, basically we have the input, then it's split somehow into the two parts, which are disjoint, and then the first part is just directly copied. The next part, we are giving the first part to the neural network, which predicts the shift and scale with which we transform that second input. Right, and this splitting into XID and XChange, it's done using the masking. And for image data sets, the masking are usually of two types. So the first type is the checkerboard pattern. So here, like red and pink pixels would go to different parts of this disjoint splitting. And for the channels-wise masking, usually what happens is that we perform a squeeze layer first. So we take an image and then, so these colors, they encode different channels into which we sort of downsample our image. So in this case, like this, first two channels would be XID and the second two channels would be XChange. And then if we condition on the first part XID and predict the parameters of the affine function for XChange, it would be equivalent to conditioning on every other row of the image and predicting the parameters for the rest of the rows, basically. And so the important thing to notice here is that when we are splitting the image into these two parts, XID and XChange, they will be visually very similar. So here, like these different channels, they are basically all downsampled images of the original image. And the same is true for the checkerboard masking. All right, so to understand what each coupling layer is doing, we visualize the learned transformation on the in-distribution fashion MNIST data and out-of-distribution MNIST data. And so here we show the output of each coupling layer together with the predicted scale and shift parameters. And this is the whole network. So we just took a two coupling layer VLNBP trained on this fashion MNIST data. And what's interesting is that we can basically see the input image both in the scale and the shift predicted in each coupling layer. And so to understand why it happens, let's look at the objective more closely. So the objective, it forces each coupling layer to predict the masked pixels in the input from the observed pixels. And the shift serves as a prediction, while the scale S serves as a sort of notion of uncertainty. So yeah, this training objective consists of the likelihood of the latent variable plus the log of the determinant of the Jacobian of this transformation. And the first term is sort of pushing Z to 0, as it will achieve the maximum value when it's close to 0. While the second term, it's large when the predicted scale is large, because the determinant of the total determinant Jacobian will be just the sum of all scales from all the coupling layers. And So we want the output of the network to be close to the mask pixels, so that and S to be large, where we are sure that we have a good prediction, and it has to be low when we are not sure that we are making the right prediction. So basically, if the T is a good approximation of this X change, then this is very, very close to 0, and we can sort of afford large values for S, and this would achieve very good values of the objective. And given that natural images, they have local structure and correlation in pixels, with very high likelihood the particular pixel will be similar to its neighbors. And leveraging these mechanisms, and given how we're splitting our input into XID and exchange using these masking patterns, the flow is able to sort of leverage this and predict the mask pixels very well, both on in distribution and out of distribution data. Another example of the mechanisms that flow use is the coupling layer co-adaptation. So we can try and prevent normalizing flow from using this information about that neighboring pixels are similar, and replace the standard checkerboard masking with the horizontal masks, which covers the top or the bottom half of the image. So in this case, it would be very hard to predict the mask pixels from the observed pixels on ORD data, as like if we train on the fashion MNIST and we can only learn to predict the sort of bottom of the shoe or skirts or dresses images, and vice versa. And we never saw something like an image of a two. But what we see in practice is quite remarkable. So for the first layer of this network, we can see that in the first coupling layer, it is indeed struggling to predict the bottom half based on the top half, and the predictions are pretty much off for both out of distribution and in distribution data. But starting from the second coupling layer and the next ones, it is making very good predictions, even for MNIST data, which it hasn't observed during training. And this is quite puzzling, because like, how can it know that based on this sort of bottom part, that this is what the top part looks like? And the answer to this is in this co-adaptation phenomena. So when the prediction is made in the first coupling layer, it encodes the information about the top half in the bottom half, and then it decodes it in the subsequent layers. And yeah, it's quite interesting, and the flows are still sort of able to co-adapt and use this mechanism equally well for in distribution and OOD inputs. Right, so we can try and affect inductive biases further by using this cycle mask, and which would make it very hard to sort of encode the information as we saw for the coupling layer co-adaptation. So in the cycle mask, the information about a part of the image has to propagate through three coupling layers before it can be used to make predictions about the same part of the image. And like, so we can mask all the 3/4 of the image, and then based on 1/4 predict the transformation for the next quarter. And so what we see in practice, that indeed this kind of mask, it does a better job of assigning higher likelihood to the trained data, to the in distribution data, comparing to checkerboard and horizontal masks. Although it doesn't fully resolve the issue, the sort of average likelihood for in distribution data is higher, and the relative ranking is better comparing to the other masks. And another approach that we try to force the flow to learn the semantic of the data was to introduce a bottleneck into this coupling layer network, or ST network, the neural net that predicts the scale and shift. So it's often a ResNet that is used for the ST network. And what we did was, for example, if we had a 4-layer ResNet, we inserted a linear layer which has a bottleneck of low dimensionality L in the middle of these ResNet. And it sort of limited the capacity of the network. And this way it cannot simply predict the mass pixels that are similar to the observed pixels, as it would require being able to reproduce pixels in the output. And with the limited capacity, it has to learn something about the train data itself. And in our experiments, these networks with low dimensional bottleneck led to better performance for OD detection. And again, this idea doesn't fully resolve the issue, but we can see that the lower the dimensionality of this bottleneck is, the better the relative ranking of the train data versus the out of distribution data. And the last part is the image embeddings. So for this experiment, we focused on, so we took image data sets, and then such as SVChan, Celebe, and CFAR, and then we extracted the sort of high-level semantic features using a deep net pre-trained on ImageNet. We train a VLNDP model on these embeddings instead of on raw pixel values, and then evaluate the likelihood histogram. So the sort of title of each graph is the name of the data set on which the VLNDP was trained on. So in this case, it was trained on SVChan, Celebe, CFAR, and in the right panel, it was trained on embeddings of the corresponding data sets. And so what we see is that typically for the image data sets, the SVChan gets higher likelihood regardless of what the trained data set was. But in the case of embeddings, the flow typically can distinguish the in-distribution and OOD data. So semantically rich embeddings produced by this deep pre-trained network make it easier for the flow to focus on the semantic content and sort of be able to distinguish anomalous data. And to sum up, the inductive biases of flows, they define performance in generalization and anomaly detection. And flows that model image distributions, they tend to leverage these generic mechanisms to simultaneously increase likelihood of all natural images, and not just those that are semantically similar to the trained data. But when we train the flow on the high-level embeddings, which sort of summarize the semantic content, we are able to detect anomalies with flows. So for more details, you can see the paper and the PyTorch code. And I guess that's it with the time. Yes, that's the end of the presentation.
Okay, thank you, Polina. So we have one question for you. So on slide 19, you say you use a low dimensional bottleneck, but where? It can't be in the map, otherwise it's not invertible anymore.
Yeah, it's not in the mapping. So the in the coupling layers, right? In this invertible coupling layers, we have the neural network that predicts the scale and the shift for 1/2 of the input. So we are copying one part of the input, and the other part we are transforming with an affine function where the scale and shift are predicted by a neural network using this XID part. And this network does not have to be invertible. So it is sort of the only nonlinear part in the flow, in this VLNDP flow. And it's able to, we don't have to make any restrictions on it. And it's usually non-invertible network that is used inside the coupling layer. And like regularly people use like just standard ResNets with a few blocks for these coupling layers, but in the experiment to understand the inductive biases, we use the ResNet with the bottleneck so that we limit the capacity of how much information can pass through this network.
Okay, I guess it was clear. Then we have also another questions that I guess also you can read in the chat, but I can read for the participant. So what do you think are the reasons why it's able to detect OEB with embeddings? Doesn't the same reason why it doesn't work for images also hold for the embeddings?
So the core reason for why it fails to detect anomalies on images is that the flow tend to learn sort of this general distribution on the all structured images. So when we're training the flow on one image data set, we can, and if we track the likelihood on other unrelated data sets, they would also increase throughout the training on one fixed data set. And because of these like mechanisms that I talked about that are like based on the flow learning to just predict the masked pixels based on the non-masked pixels. And like, because this would work for basically any structured data, as we have similar pixels in the sort of local regions of the image. But for the image embeddings, so they're just like sort of vector tabular data that somehow summarizes the information about the image. And like the network that was used for feature extraction here was the network pre-trained on ImageNet. And the first layers, they are sort of serving as, I don't know, edge detectors, and like some, they contain already some information about and summarization of the information of what is in the image in the discriminative sense. So like which objects are in the image maybe. And that is like a better sort of signal for how to distinguish between the trained data and like anomalous data. So yeah, does this answer the question or?
Yes.
I think so.
Yeah, okay. So the author said yes in the chat, so thank you.
Is there any more questions from the participants?
Yeah, if you have other questions, feel free to unmute yourself or write in the chat.
Yeah, also if you have questions after the seminar, you can definitely reach out and we can chat afterwards.
Thank you so much, Polina. So,
yeah, thank you. I will stop sharing.
Okay, perfect. Thank you.
So we will continue with the very last speaker, Antoine. So Antoine, if you're ready, you can.
Yeah, I'm trying to share my screen.
Okay.
Oops. Can you see my screen?
Yes.
Perfectly.
Okay. Okay. So first let me thank you, Alison and Federico for having me, and also thank you, Polina and Dimitris for the nice talk. So I'm very glad to talk about normalizing flows and Bayesian network here for the next 20 minutes. So first, we may agree on the fact that normalizing flows are becoming more and more popular recently. And maybe this can be partly explained by the fact that in contrast to other generative models, we have access to the model's likelihood. And so this provides a good loss function and may also be used to compare different normalizing flow models, even if there are some drawbacks, as Polina explained. Another great advantage of normalizing flows as density estimation methods is that some architectures have been shown to be universal density approximators of continuous random variables. As an example here, you can see in the first row 5 2D datasets whose density is multimodal or almost discontinuous and with complex shapes. And you see in the second row, the density learned by a normalizing flow. So you see this is almost perfect. And in the last row, you see new samples generated with the flow, and they match well with the training data. So even if it's just 2D examples, we see here the capacity of this kind of models. And maybe probably the best explanation why these models are gaining in popularity is just because they work well in practice. So even for data in high dimensionality, such as images. So for example, here you see the results of GLOW, which is a flow architecture designed for images, and that is trained there for a celeb-A dataset. Nevertheless, flows are not perfect yet. So I think, in my opinion, one big obstacle when using normalizing flow is to decide which architectures to use. So Polina talked about coupling layers, Dimitris about autoregressive, and maybe also manifold flows. So there is a lot of different possibilities, and you can even combine these different possibilities. But in general, it's not easy to know which one to select. And so another drawback of flows, I think, is that they are kind of black box. Even if I don't really like this expression when talking about neural networks, but we must admit that understanding the hypothesis made on the data distribution modeled by a flow is not often easy. And so these two drawbacks combined end up in a poor inductive bias. So indeed, the fact that we cannot easily understand why maybe the model is not working as expected or as we would like makes it harder to iterate on the architecture choice and to find maybe the architectural modification that would improve the model. Of course, the problem I mentioned is not completely unsolved. So as an example, I showed you good results for images. So this one were based on coupling layers and other tricks. But you can, so I will come back to these kind of layers, but Polina, as Polina explained, these layers makes a strong assumption on some independence between the components. And thanks to that, you are able to combine that with checkerboard masking and maybe channel masking, such that you hope to have something that is good for images. Similarly, if we are working with time series, we can use maybe autoregressive architectures. So there we do not make any independent assumption, but we kind of say that the non-randomness of the future can be predicted from the past. And so maybe this can be a good inductive bias when working with time series. But when you are working with simple tabular data, then there is no architecture that will particularly put a good inductive bias. And so even if there are architectures that are able to take into account symmetries and so on, but they are not really helping with tabular data. And so at the end, it's not easy to design the architecture and to understand the modeling assumptions, except for some cases. Sorry, so on the opposite, one class of models that have been popular to model the joint probability distribution of tabular data are Bayesian networks. So these are probabilistic graphical models that were formally introduced by Pearl and collaborators in the 80s. And so these models visually depicts through a directed acyclic graph the factorization of the distribution that you want to model. And we can read the graph to check whether or not some independencies are hypothesized by the model. For example, if we take a vector of dimension 4, we could assume the following Bayesian networks because it could make sense for the data. And this would be equivalent to assume some factorization that is shown in the slide. And then we can use this Bayesian network and an algorithm which is called d-separation to see that this factorization and the assumption on the model implies that x1 is independent from x3, given x2 and x4. And so this kind of model can be useful because it makes it easy to read the independencies that you are assuming with your model. So these models have also good and bad sides, of course. One good side is that these models are good for modeling independencies, as I said, and check their global impact on the model density. They're often used to reason about problems and even in real world applications. So they are really used. So this kind of model can be good only for theoretical reasoning, but they're also used in real application if we take the time to model the different conditional probability factors. And regarding the drawbacks, I think one is that real-world application usually rely on either discrete data or discretized data. And so it makes so kind of outdated with respect to the deep learning revolution, which is trying to use very large data sets and continuous data. So this is maybe why it's becoming less popular with time in comparison to deep learning. But what is interesting is that the factorization that you imply with some flow layers can be expressed by a Bayesian network. So to be precise, when we use an autoregressive layer to transform a base latent vector U into a vector X that follows a target distribution, we model each output Xi as a function f of the corresponding component Ui of the base vector. The function f is invertible with respect to Xi and is conditioned on the previous component of all the base vectors. So in other words, we condition the invertible transformation f. I will call it the normalizer in the rest of this talk. We condition this normalizer with the output of a function Ci of the input vector U. And if we talk about autoregressive layers, this function Ci only depends on the first ei-1 components of the input vector. So this is the assumption that you make when you use autoregressive layers. And in 4D, this is equivalent to assuming the following Bayesian network. And if you have only one step of flow, and that you are using a latent distribution that is composed of independent components, then it's equivalent to modeling each factor of the factor distribution. And I won't go into the detail, but you can show that this is also valid for coupling layers. So you can model the coupling layers as being a specific Bayesian network. And so this all means that two of the most commonly used layers in the flows architectures can be seen as Bayesian networks with a very specific topology. And so then comes the question, can any Bayesian network lead to a normalizing flow layer? So the answer is yes. I would not be talking here if it wasn't, but indeed you can imagine that you may use a flow to model each of the factors defined by the Bayesian network. And so this is what we have done. So in particular, so if you are given an hypothesized Bayesian networks, so that could be the autoregressive or coupling layers, but it could as well be other assumptions that would make sense for the data you are playing with. So we define the graphical conditioner as a free-form function h of the one-by-one product of the base vector u with the row I of the adjacency matrix that corresponds to the Bayesian network. So this adjacency matrix is a matrix where an element ij is equal to 1 if and only if the node j is a parent of the node I. And so at the end, this transformation is just equivalent to masking off the element of the vector u that are not a direct ancestor of the node I. Okay, so you are just keeping the information of the direct ancestor of the node I. And so now, instead of conditioning either with autoregressive or coupling architectures, you can condition with any Bayesian networks that could make sense for the data you have. So is this useful in practice? So yes, because making assumption with Bayesian networks may be useful in practice. So just for this reason, it may be useful. For example, if you are to model a data set about people and their salary, you could like maybe to ensure that gender and salary are independent from each other. In a perfect world, it's not like that, but maybe it could make sense at some point. And it's not only useful because you would like to ensure some independencies, but it's also useful if you know that some independencies are in your data, because it will then put a good inductive bias on your model. So as an example here, if you look at the plot, you have the y-axis, which is the likelihood of the model, and don't care about the x-axis for now. So the red line is the likelihood of a graphical layer. So this is the layer I just introduced with a Bayesian networks that was correct for the data we had in hand. And the green line is an autoregressive layer. And so you see that the graphical layer leads to the best performance. And this is probably because making the right independent assumptions and forcing the model to ensure them helps learning a better model with a smaller amount of data. And so, of course, you are not always given a Bayesian network of the data. So it may be a bit worrying to be forced to define this Bayesian network. So what you can do, in fact, is to learn it from the data. So you will learn the directed acyclic graph such that its adjacency matrix, when it is put in the graphical conditioner, will create a normalizing flows that fits at best your data. So if we define formally this optimization problem, we look for the adjacency matrix A such that some score function that is a function of A is maximized. And here the score will be the likelihood of the graphical normalizing flow associated with the adjacency matrix. And then you end up with this kind of maximization problem under a combinatorial constraint. Why combinatorial? Because it requires you to find the best subset of edges. So it may first seem very complicated to solve this kind of optimization, but good for us. We can we formulate the combinatorial problem into a continuous constraint. If we relax the adjacency matrix to contain real positive values instead of Booleans. And so this matrix will be such that a value of 0 in the cell ij, for example, means that there is no edge from the node j to the node I in the associated Bayesian network. And else, if the value of the cell is non-zero, then the connection from j to I will be as strong as the value is large. So as strong in terms of Bayesian networks, it doesn't make any sense, but in terms of directed acyclic graph, you imagine that it just means that the information is flowing better if the connection is strong. And so then we can reformulate the acyclicity constraint as a function W of A that is large, that is as large as there are paths with strong connections to go from a node to itself. So it means that when the graph is not acyclic, so the graph is cyclic. And so here you can see, for example, that the value of WA in the left graph will be very high because the edges that must be used to go from a node to itself are large. Then it will be a little bit smaller in the middle graph because these edges are thinner. And it will be exactly 0 in the white one because it does not contain any cycles. And so at the end, we can use now this continuously constrained problem to solve, to use Lagrangian formulation and solve it with usual tools such as gradient descent. Of course, this has a computational cost. In particular during the training phase, because this optimization takes some time to converge from something that is not acyclic, because we start with a graph that is fully connected. We do not make any assumption about any independencies. But as we start from this completely cyclic graph, it takes time to find a good acyclic graph that reaches good density estimation performance. However, once the Bayesian network has been found, at test time, this is as fast as autoregressive or coupling layers. And while it can reach performances that are on par or even better than autoregressive layers, as you can force some kind of sparsity in the Bayesian network, then you will be able to invert your model faster than you are able to do with autoregressive layers. So now let's have a look at some results when we learn the topology with this constraint optimization. Left, you see the result for an artificially generated dataset made of 8 pairs of independent variables. So we just took 8 datasets of 2D datasets, and we concatenated them. And these 2D datasets were datasets that looks like the first images I showed you with the complex distributions. And on the left plot, so you see the log likelihood of the model as a function of the sparsity of the recovered topology. So we can force the sparsity by using some L1 penalization on the adjacency matrix. In red, you see again the result with a perfect adjacency matrix that makes the white independence assumptions. And in green, you see the results with an autoregressive layer. And you see that learning the topology may improve with respect to autoregressive layers, and that we may reach results that are almost as good as if you were given a correct Bayesian network. And on the white plot, we show one correct adjacency matrix for this problem. So this is the black cells. The gray cells are just the transpose of the black ones. It's just because if you have a connection in one direction, you could say that maybe you have something that makes sense also in the other directions. And the stars denotes the connections that have been recovered by the optimization. And so you see that the optimization is able to find all the dependencies that were in the actual data. And it's also able to remove the spurious connections. So at the end, it's doing a perfect job on this simple task. So this was more or less a toy example, but does it work well in practice in some more realistic settings? And so what we do here is to benchmark a normalizing flow made of only one step of graphical conditioner in which we learn the topology. And we benchmark it against the most commonly used flow architectures. And you may observe, so our results are in the first row, and you may observe that we reach quite competitive performances, even if we use only one step of transformation, and that we have something that may be at the end interpreted as a Bayesian network, so we can really read some independencies and so on. We reach quite good results. And this is interesting because this shows that we are able to have a density estimation that is almost as good as kind of black box models, with a model from which we can easily understand and force some independencies. So to conclude, there are still area for improvements. So I think one interesting direction would be to see if it's easy to keep these independencies when you combine multiple steps of flows. Because here I showed only results for one step flows. And this is okay if you use a very expressive normalizer, but if you use, for example, affine normalizers, then you will quickly see that you are lacking some capacity in your transformations. Also, how could we maybe handle only a partial knowledge of the independencies? So putting some kind of prior knowledge on the Bayesian networks, but not saying either we know it or we do not know it at all. And maybe it could be also interesting to see how we can combine the flows, and maybe in particular the graphical normalizing flows with causal reasoning, because Bayesian networks are usually used to do causal analysis and causal reasoning. And so here we have a nice tool to bridge the gap between the two. And if you want to know more details about this work, you can check either Graphical Normalizing Flow, which is a joint work with my advisor, Gilles Loup, that really go into the details about the architecture. And the other paper is more about an analysis of what we can understand from coupling and autoregressive layers if we analyze them through the lens of Bayesian networks. And that's it for me. Thanks.
Thank you, Antoine. So, as always, if you have questions, feel free to unmute yourself or write in the chat.
Yeah, it was a very, very nice talk. Do you already have some hints about your perspective? Do you, like, for instance, do you know if we could benefit from
no, so for the first one, I didn't really dig into it. The last point, I know that people are trying to learn Bayesian networks and to do some causal reasoning with them, but I think there are still a lot of work to do to make something that is really making sense in terms of causality. And about the partial knowledge, I didn't find anything, so.
But yeah, otherwise it was a very nice talk.
Okay, thank you.
So,
yeah, I guess. Okay, there is like one question. If you have any link with the structured lasso?
Not really, no. I'm not sure what Nicola is trying to say by structured lasso. Just the L1 penalization, or is it something more specific to flows? Or I don't think so, but if you want to discuss that in private, feel free to reach me. Okay.
Yeah, feel free to unmute yourself, Nicolas, and follow up.
okay.
Okay, perfect.
Okay, cool.
Okay, so
I guess this will be the end of the seminar. So thank you so much to all the speakers who participate to the seminar. And thank you also to the participants for all your attention. And
yeah, it was the first time we were trying to make this seminar online, so we have a lot to learn, I guess. So I hope the next one will be like more like we can improve ourselves also in organizing the questions and everything. But thank you very much to all the speakers and also the participants. Thank you.
Thank you for organizing.
Yeah, thank you very much for organizing and inviting us.
Thanks so much. Thanks so much. And have a good one.
Perfect.
thank you, everyone.
We will end the meeting now. So
Bye.
bye.
Bye.